Hello student, functional analysis paper number 13 unit 2. Let X be a non-linear space over field complex field. Script C of X is the set of all bounded continuous function on X. Then script C of X is norm algebra under these operations. We have to prove script C of X is norm algebra under these operations. F G belongs to script C of X. First, F plus G of X is equal to F of X plus G of X. Pointwise addition, scalar multiplication, and multiplication. F plus G of X is equal to F of X plus G of X. Alpha into F of X is equal to alpha F of X. F into G of X is equal to F of G of X. And norm defined as norm F is equal to supremum of norm F of X such that X belongs to X, norm X is less than or equal to 1. Solution. From first and second condition, it is linear, and from first three conditions, we can say script C of X is an algebra. Next, now norm F of X is equal to supremum of norm F into G of X, where such that X belongs to X and norm X is less than or equal to 1. By this, by definition of norm F is equal to supremum of, by third condition, F into G of X multiplication, where X belongs to X, norm X less than or equal to 1. Give separate norm F into norm G of X because of norm T of X is less than or equal to norm T into norm X is equal to norm F bar ले ले into supremum of norm G of X, where X belongs to X, norm X less than 1. This is the definition of norm G. So norm F into G is less than or equal to norm F into norm G. So script C of X is a norm algebra. Now I belongs to script C of X, where I of X is equal to X for every X belongs to X. By definition of norm F is equal to supremum of norm F of X such that X belongs to X and norm X is less than or equal to 1. Put F is equal to I is equal to supremum of F of X. So I of X such that X belongs to X and norm X is less than or equal to 1 is equal to supremum of, put the value I of X is equal to X. So supremum of norm x where x belongs to x and norm x less than 1. So this is equal to 1. So norm I is equal to 1. So script c of x is a norm space with identity. Now, if X itself is a Banach space, then script C of X is equal to B of X is equal to BXX is Banach algebra. Complete the proof. Because of script C of X is equal to B of X and B of xy. If x and y are Banach space, then B of xy is Banach space. So B of xx is a Banach space if x is Banach space. Not. A is defined Banach algebra. G is defined the set of all regular elements of A, and S is defined as the set of all singular elements of A or non-regular elements of A. Theorem 1. Let A be a Banach algebra and let X belongs to A if norm X minus 1 is less than 1, norm X minus 1 is less than 1, then X belongs to G, means regular elements. X is regular. If X is regular, then inverse exists, and X inverse is equal to 1 plus summation n is equal to 1 to infinite 1 minus x raised to n. We have to prove X is regular and inverse is equal to this. So we let yn is equal to 1 plus summation k is equal to 1 to n minus 1 into 1 minus x raised to k. Then for n and p belongs to n. So now yn plus p minus yn is equal to yn plus p is equal to 1 plus summation k is equal to 1 to n is equal to n plus p minus 1 of 1 minus x raised to k, and yn is equal to this. So subtract yn plus p minus yn is equal to 1 cancel out, n is summation n in the summation the value value of yn is k is equal to 1 to n minus 1 cancel out, so k is equal to n to n plus p minus 1 of 1 minus x raised to k. Now we take both the side norm, so we get norm yn plus p minus yn is equal to summation k is equal to n plus p minus 1 of 1 minus x raised to k. Now simplifying this, we get norm yn plus p minus yn is less than or equal to summation k is equal to n to n plus p minus 1 of norm 1 minus x raised to k. If we put the value of k, we get norm 1 minus x raised to n plus norm 1 minus x raised to n plus 1 plus up to plus norm 1 minus x raised to n plus p minus 1. So in this summation we common out norm 1 minus x raised to n. So we get 1 plus norm 1 minus x raised to 1 plus norm 1 minus x raised to 2 plus up to 1 minus x raised to p minus 1 is less than or equal to norm 1 minus x raised to n into 1 plus norm 1 minus x plus norm 1 minus x square plus up to infinite is equal to, this is of the form 1 plus r plus r square plus up to infinite. So and r is less than 1, so the formula a upon 1 minus r, so a is equal to 1, 1 minus r is equal to norm 1 minus r. Now n tends to infinite, this is value, the value of norm 1 minus x is less than 1, is less than 1, so n tends to infinite, this tends to 0, so sequence yn is a Cauchy sequence in A. Since A is complete, A is complete because A is Banach space and a complete nonlinear space is called Banach space, so A is complete. Yn tends to y in A, so y is equal to limit n tends to infinite yn. So y is equal to 1 plus summation n is equal to 1 to infinite 1 minus x raised to n, equation number 1. Now y minus xy is equal to 1 minus x into y. Now put the value of y from the equation 1. Now put the value of y from equation 1, we get this 1 minus x into 1 minus summation n is equal to 1 to infinite 1 minus x raised to n. Now multiplying 1 minus x, so 1 minus x into 1 is equal to 1 minus x plus summation n is equal to 1 to infinite 1 minus x raised to n into 1 minus x, so 1 minus x raised to n plus 1. Now simplifying this, we get 1 minus x plus 1 minus x square plus 1 minus x cube plus up to infinite. So we write in the summation form, summation n is equal to 1 to infinite 1 minus x raised to n. So the value of y is equal to 1 plus summation n is equal to 1 to infinite 1 minus x raised to n. So summation n is equal to 1 to infinite 1 minus x raised to n is equal to y minus 1. So y minus xy is equal to y minus 1. So y cancel, minus minus cancel, xy is equal to 1. Similarly, we can prove that yx is equal to 1. So xy is equal to yx. So this is commutative algebra, and so x belongs to G, that is x is regular. So x inverse is equal to y is equal to 1 plus summation n is equal to 1 to infinite 1 minus x raised to n. Xy is equal to 1 and yx is equal to 1. So y is equal to x inverse. This is complete the proof. Now corollary 1. Let A be Banach algebra. Let x belongs to A. Norm x less than 1. Then 1 minus x belongs to G. So we have to prove 1 minus x is regular. 1 mi If 1 minus x is regular, then inverse exists, and inverse is equal to 1 minus x inverse is equal to this. We have to prove this and this. We let norm x is equal to 1 minus 1 minus x. This is of the form norm 1 minus x but x is equal to 1 minus x. Norm x is less than 1. Norm x is less than 1 given. We know this theorem. If norm x minus 1 is less than 1, then x belongs to G. This is 1 minus x is less than 1. So x is equal to this. So so x belongs to G. X is regular. So 1 minus x is regular, and inverse is equal to 1 minus x inverse is equal to, put the value x is equal to 1 minus x. So 1 minus x inverse is equal to 1 plus summation n is equal to 1 to infinite 1 minus x is equal to 1 minus x. So 1 minus 1 plus x, this cancel, is equal to x. So x raised to n, hence the result. Let A be a Banach algebra and x belongs to A. Let lambda belongs to C. If norm x is less than mod lambda, then prove lambda dot 1 minus x belongs to G. Means lambda into 1 minus x is regular. Let proof. Let norm x less than mod lambda, we know that mod norm lambda is equal to mod lambda. So આ બાજુ લઈ જઈએ તો norm x upon norm lambda. So norm x upon lambda is less than 1. By previous corollary, norm x less than 1, then 1 minus x belongs to G. Here x is equal to this. So 1 minus x belongs to G. So 1 minus x upon lambda belongs to G. So lambda multiply करिए तो lambda minus x belongs to G because of invertible element is equal to scalar into invertible element. Now here corollary 1. Here 1 minus x ની જગ્યાએ મૂકવાનું પુટ કરવાનું છે આપણે x upon lambda. So here x raised to n. So x upon lambda raised to n. Multiply this lambda into 1. Lambda into 1 minus x. Lambda multiple માં lambda into 1 minus x upon lambda raised to minus 1. So we can write into lambda is equal to 1 plus summation n is equal to 1 to infinite x raised to n upon lambda raised to n. So lambda raised to minus n into x raised to n. હવે lambda આ બાજુ આવશે તો lambda આ બાજુ આવે તો lambda raised to minus 1. Simplifying this, n is equal to 1 to infinite. If we take n is equal to 0, so x raised to 0 1. So we can write n is equal to 0 to infinite lambda raised to minus 1 minus n minus 1 x raised to n. So this is lambda into 1 minus x raised to minus 1 is equal to n is equal to 0 to infinite lambda raised to minus n minus 1 into x raised to n. Complete the proof. Thank you.